Hello, George Diamond again. We're getting ready to finish our unit in AP Calculus on derivatives, and the last thing we'll be looking at here is related rates. Now, starting off my video, I'm carrying a container of salt. This has absolutely nothing to do with our video, other than the fact my students that are watching the video should document anything that's unusual about the video, because I may ask them about what I'm carrying at the beginning of the video tomorrow in class. So I'm going to put this aside. It has nothing to do with our video. I said in our textbook now, this is section 2.6. We use the Larson text. So this is section 2.6, and this finishes up our unit here. This is chapter 2 in our book. And we'll look at something called related rates. So to start off, we have a couple of essential questions. Okay, first, what is a related rate? So we'll look at this. Second, how do you use related rates to solve real-world problems? All right, now we're going to be in this PowerPoint here. I'm basically going to be standing in front of the PowerPoint, kind of describing some information about related rates. We're not going to look at a bunch of examples in this video. Now, in the next video, we're going to look at 4 or 5 examples. All right, so, but in this video here, we're not going to be looking at that many. Okay, first, what is a related rate? Now, related rate, this is the rates of change of 2 or more variables with respect to time. Okay, this is what a quantity expressed in terms of a function or an equation. It could be a formula of some type, or something is changing over time. And this is what a related rate does. So it shows how 2 or more variables are changing with respect to time. So when you take the derivative now, we already know how to do implicit differentiation. So when you take the derivative with respect to time now, you're taking the derivative with respect to a different variable. So when you take the derivative, you're going to start off with d over dt of whatever it is you're taking the derivative of, whether it's x, y, or whatever. So let's get started with a little bit of information here. So first, let's see if we can find the derivative with respect to time of just a little cubic function here. So y equals 2x to the 3rd power. Now, we're not going to do anything with it. Okay, we're just going to use implicit differentiation to find the derivative with respect to time t. Now, to get started, let's do the y variable first. Okay, let's express the rate of change of y with respect to time. And that would be the derivative, which would be dy over dt. So that's the rate of change of y with respect to time. Now, as you take the derivative of the right-hand side, we're going to take the derivative of 2x to the 3rd power. Okay, with respect to time also. So you take the derivative, use implicit differentiation. The derivative of 2x to the 3rd is 6x squared. Make sure you remember to subtract 1 from your exponent when you take the derivative, and then times dx over dt. Remember, we're using implicit differentiation here to take the derivative. So this would be the derivative of our cubic function here with respect to time t. And once again, like I said, this is a form of implicit differentiation. Take the derivative of y with respect to time, and take the derivative of the x expression with respect to time. Yet you have to remember now to leave dx over dt as a factor. Okay, let's try another problem. Let's look at the next one. Okay, let's try one way to do a little bit with. Now this is sort of like what we'll see in our homework when we get into our homework. It says, with this problem, it says, we bring up our function. Here it is. This time we're going to do a parabola. It says, find dy over dt when x is equal to 1. Given that dx over dt equals 3 when x is equal to 1. Right. Now, as we take our derivative here, let's start off, let's find the derivative with respect to time t. And with this type of problem, we're just basically substituting in once we find the derivative of our equation. Okay, let's do the derivative of y with respect to time. This would be dy over dt equals, now the derivative of x squared would be 2x times dx over dt. So we're going to take the derivative of both sides of your equation or your formula, whatever it is you're working with respect to time. It says we want to find dy over dt. So we're looking for this right here, the left-hand side, dy over dt, when x is 1 and dx over dt is 3. So now it's just a matter of substituting in. All right? So to get dy over dt, okay, now this should be equal to 2 times x. Now x is 1. And dx over dt is 3. So it's just a matter of substituting this in. And then multiplying 2 times 1 times 3 gives us 6. All right, so the rate of change of y with respect to time is 6. So when you think about it, this is 6 units, whatever, with respect to time. Time could be seconds, minutes, hours, whatever. But the rate of change of the y variable with respect to a time unit of some type. Okay, let's move on. So this is another little example. Now in the next video we'll be doing some actual applications of some formulas and things. So let's take a look at some steps that we're going to use for working related rate problems. Now some of these problems, you can with some of these applications of related rates, they're all different pretty much. We're going to do 4 or 5 examples to kind of give you some idea of what they're like. But a couple steps that we can use to solve related rate problems. Okay, first, draw a picture. If they're talking about a formula, if they're talking about a circle that's increasing, if they're talking about a triangular relationship of some type, you always want to start off by drawing a picture, a diagram, a sketch, something like that. So that's the first step. So it kind of gives you some idea of what you're working with. All right, so draw you a picture. Number 2, write down any known information. Now in the problem, what do you know? Okay, do they give you any rates? Do they give you any time? So write down any known information that you're given. Okay, write down what you're looking for. Are they asking for the rate of change of the area with respect to time? Right, so you need to write that down. You're finding dA over dt. Right, so what are they looking for? You want to write down what it is you're looking for. Also, write an equation to relate the variables. Now, a lot of times this could be a formula from geometry, and we're going to be looking at several of those. So you're going to write an equation that's going to relate those 2 variables, or it could be 3 variables possibly, depending upon what type of relationship you're looking at. Number 5, differentiate both sides with respect to time, and then last, you're going to evaluate it. So at the end, you're going to plug them in, substitute your values in, and then find what the actual rate would be with respect to time. So 5 steps. If you can follow these 6 steps actually, you can follow these 6 steps, you can work most related rate problems, right? So about any related rate problem. Okay, first draw a picture. Okay, if a picture is appropriate, you want to start off with a diagram or a picture. Write down any known information. Write down what you're looking for. Then you're going to come up with an equation that's going to relate your variables, right? And then you're going to take the derivative of both sides with respect to time. Last, you're going to evaluate it. Now, next, let's take a look at some modeling, some statements here that we'll see in the next video possibly. Now, these are also in your textbook, so you can kind of follow me in your book if you want to as we take a look at each one of these. Now, here's our verbal. I'm going to give us a verbal statement, and we're going to see what the matching mathematical model would be, because we're modeling each of these statements. So to get started, so we have the velocity of a car traveling for 1 hour is 50 miles per hour. So the velocity, now velocity is the first derivative. Traveling for 1 hour is 50 miles per hour. Now this is our verbal statement. Now we're going to convert this into a mathematical model. Now first, let's let x equal the distance traveled. So if x is the distance traveled, so we're talking about the velocity. This would be the rate of change of x with respect to time. So it'll be dx over dt equals 50 when t equals 1. So as you look at this, if this were in a reading problem or an application problem of some type, okay, this is what we're given in this verbal statement. Right? So you got to be able to read the question and see that you're actually given the rate of change of x. If x is the distance, the rate of change of x with respect to time. Okay, let's try another example. Here's our verbal statement. It says water is being pumped into a swimming pool at a rate of 10 cubic meters per second. Right, so here's our verbal statement. So water is being pumped into a swimming pool at a rate of 10 cubic meters per second. Now, what would be the appropriate mathematical model? Now, first of all, you want to notice what's changing here. So water is being pumped into a swimming pool. So the water's, so basically the volume of the water in the pool is changing, right? So in this case, we're going to let V equal the volume of the water in the pool. So, if you're pumping water in, the volume is getting bigger, is increasing, right? So let's let V represent the volume of the water in the pool. So the rate of change of the volume with respect to time, all right, with respect to the seconds, would be dV over dt equals 10 cubic meters per second. So if you were to see this in an actual reading problem now, you got to recognize that what we're talking about here is the volume. That's nothing more than the volume, so the rate of change of the volume, as he described the 10 cubic meters per second. Okay, like I said, this is a short little video here. This is the end, and in the next video we'll look at some 4 or 5 good examples. Hopefully that will give us a better idea and a better understanding of some applications of related rates.